Hi, and welcome to H2.3 Moment of Inertia. In this lesson, students will be able to calculate the moment of inertia of several objects. Before we talk about moment of inertia, let's talk about analyzing net torque because it'll bring to us the importance of knowing this. What the heck is moment of inertia? All right, so when we studied net force in linear dynamics, there were only two possibilities for the net force. Either the object was in equilibrium, and that's when the velocity didn't change, it was at rest or a constant velocity. There was no acceleration because the forces are balanced, and the net force was equal to 0 newtons. If it wasn't in equilibrium, then the velocity is changing. There is acceleration because the forces are not balanced, and the net force was equal to m times a. Okay. Well, when analyzing the net torque that arises from forces trying to cause a rotation, or torques, two similar possibilities exist. Either the object is in equilibrium and the angular velocity doesn't change. It's at rest or a constant angular velocity. There is no angular acceleration because the torques are balanced and the net torque is equal to 0 Newton meters. If the object is not in equilibrium, then the angular velocity is changing. There is angular acceleration because the torques aren't balanced, and the net torque is equal to, not ma, can you guess what the net torque is going to be equal to? I alpha. So maybe you got alpha, right? Because they're acceleration, and then alpha is the angular acceleration. Before we analyze rotating systems that are not in equilibrium, let's study this mysterious I, which is known as the moment of inertia. See how inertia and, well, it was over here before, but mass, right? Mass, inertia, mass is a measure of inertia. So I, or the moment of inertia, is like rotational mass. So here it is, the last row in our column of similar things for dynamics. Or is it? Are we going to add in more? What did we do after we did dynamics? I don't know. But anyway, F is equal to ma, as the torque is equal to I times alpha. Tau equals I alpha. Okay, so before we get into the equation for moment of inertia and all that stuff, there's typically a nice demonstration that I like to do in the classroom. You have a hoop, so this is our hoop, and you have a solid disc of equal mass, so they're the same mass, and they're the same diameter. It doesn't say it on the problem, but they're the same exact size, same exact mass, but this one is hollow on the inside, and this one's solid. They're released from the same height, from the top of an incline. What do you think happens next? Pause the video and think about it. Maybe you said they reached the bottom at the same time because they're the same diameter, they're the same mass. Maybe you say one reaches the bottom faster than the other. Maybe you say they jump off of the incline and into the sky. No, maybe not. To answer this question, let's learn more about rotational mass, or the moment of inertia. Because yes, if you put these on a scale, they would have the same mass, but the orientation of that mass around the axis of rotation is different. This has more mass further away. This has more mass closer to the axis. So the orientation is different. How the heck do you handle that different orientation of different rigid bodies? It's by studying the moment of inertia. We use a capital letter I to represent the moment of inertia. So think of what we know about inertia as I read the definition. It says a quantity expressing a body's tendency to resist angular acceleration. You can think of it as rotational mass because we said that mass is a measure of inertia. And Newton's first law, as a reminder, do you know Newton's first law? An object in motion stays in motion with constant velocity in a straight line, and an object at rest tends to stay at rest unless acted upon by a net external force, which would cause that acceleration. But the tendency of body to continue doing what it's doing. Okay, and now we're talking about in a rotational frame. The units for the moment of inertia is a kilogram times a meter squared, kilogram meter squared. So knowing the units, can you think what might the equation look like? So I, the moment of inertia, is equal to your mass, that's where the kilograms come from, times the radius squared. But this formula is only for a particle. We have the mass located at one point, and it's a certain radius away, okay? But on the previous slide, we talked about how that mass can be oriented in different parts around the rigid object, all right? So how can we handle it if there's a different shape, not just a particle? How does the arrangement of the mass of a rigid object affect how it will rotate? You could have a solid cylinder or a hoop where, again, the mass is further away from the axis. You could even have a rod rotating about its center like this, or maybe even a sphere like Earth, a solid sphere, or maybe it's a hollow sphere like a ball, like a basketball. And then how does the axis of rotation, because remember I is equal to mr squared, so depending on where the axis is, that will change the equation for the moment of inertia as well. So instead of an axis about like it's rolling, what if it's spinning around like a quarter? Same with this hollow hoop. And what if the rod's not rotating about its axis in the middle, but swinging around one end? Luckily, we don't have to derive those formulas or memorize them, but each different situation has a different formula associated with it. So where are the equations for the moment of inertia of various rigid objects rotating about different axes? It is on the bottom of our rotation page. You can see here, this is the equation that I just gave you for the particle. And for the hoop, it's still mr squared. But if it's a solid disk, it's 1/2 mr squared. And for the rod, about its center, it's 1/12. And L is just the length. So sometimes we won't write R. If it's the length of the rod, we'll put L. And then you could have a solid sphere rolling or a thin-walled solid sphere rolling, and you could have 2/5 and 2/3. So there's all these different equations, and you'll read the word problem and then you'll match it up with this depending on what the situation is. So now we have some more information about this disk and hoop situation, okay? Pause the video and think what will happen when you release them from rest. If you need a hint, think about how mass affected acceleration when we did Newton's second law. That's a pretty good hint. Pause the video and think about it. What do you think will happen? Did you pause it? We'll see. Okay, so I'm going to let them go. And what do you think is going to happen? Whoa! The solid cylinder reaches the bottom first. It had a greater acceleration. Let's see why that is. Newton's second law says that the force is directly proportional to the acceleration, and the acceleration is inversely proportional to the mass. We're going to do the same thing in the future, all right? But this lesson's all about this I. So we don't have to really calculate it yet, but we should have a fair idea of what's going to happen. Since the acceleration is inversely proportional to the moment of inertia, that should give us some clue as to what will happen. Which one has a greater moment of inertia? Can you predict just by looking at the formulas? We said they have the same mass, they're the same size, so those are the same. What's the difference? The moment of inertia is half as great for the solid disk. So if the moment of inertia is smaller for the disk, that means it's greater. It's an inverse relationship. The angular acceleration is greater for the solid disk, which is why it reaches the ground first. Interesting. So let's do an example. I'm dying to know, what is the moment of inertia? Can we please calculate something? Okay, it says the mass of the hoop and disk in the demonstration is 1 kilogram, and the diameter for each is 10 centimeters. What is the moment of inertia of the hoop? And what is the moment of inertia for the disk? And then I want you to compare the two moments. That's like a fancy way of saying, you could say moment instead of moment of inertia. How does this correlate with the result from the demonstration? Is our calculations going to match our prediction and what we saw in the classroom, but on the animation just there? So you could pause the video and try it on your own. So let's start by just looking at the hoop. The hoop has a mass of 1 kilogram and a diameter of 10 centimeters. Wow, thanks for telling us that. That means that the diameter is really 0.1 meters, and that means the radius is half of that, 0.05 meters. Tricky. Sometimes they'll give you the diameter, just try to be like, are you paying attention? So keep an eye out for that. So we look at our reference table, and we see that for the hoop, the moment of inertia is equal to the mass times the radius squared. So the moment of inertia is equal to 1 kilogram times 0.05 meters squared, and you get 0.0025, but really we write it like this, 2.5 times 10 to the 1 to negative 3. And then again, this is a kilogram times a meter that's being squared. So kilogram meter squared. Okay, let's see how that compares to the disk. I was about to say cylinder. I guess it's the same. Disk, same mass, same diameter, same radius. But now the mass is being oriented around the axis differently, and the way we account for that is by looking in our reference table. So I is equal to 1/2 mr squared for a solid cylinder or a disk, it says right in the reference table. So I is equal to 1/2 times 1 times 0.05, and then don't forget to square that radius. And as you might expect, it's just half of the moment of inertia that we got before, 0.00125, or 1.25 times 10 to the negative 3 kilogram meters squared. Wow, maybe it's a little easy to compare these because they are in scientific notation. You could see that this one is half as great as this one pretty easily. Thanks, scientific notation. It's good stuff. So, yeah, does this correlate with the result from the demonstration where the disk reached the bottom first? I would say so, because if you think of the rotational type of stuff, you could say like this has less rotational mass than this one does. It has less of a moment of inertia. So since it has less rotational mass, the same torque will accelerate it faster. We're thinking Newton's second law again. All right, so we'll give it a nice big green check mark. Nice, it does correlate. You could get some interesting problems here too. Not that that wasn't interesting, but like some really cool ones. So the example 2 says a baton consists of a 0.5 meter long rod. That looks familiar. There's a rod in the reference table with a ball on each end. That does not look that familiar because in the reference table, they give you this with the axis like this. But you're not rotating around the ball like that. All right, the axis is over here. So what the heck do you do? If it's a ball, sometimes you can just approximate it as a particle. All right. So think of a particle, and normally it says it at the end over here. It'll be like, treat the ball like a particle. And then you could just use I is equal to mr squared. So that's the game plan for that. If you want, you could pause the video and try to think about how you would solve for this one, because it's a little bit of an added step, I guess. Let's read the whole problem first. So it says the rod has a mass of 1 kilogram and the balls have a mass of 1 kilogram each. What is the total moment of inertia of the baton when it's spun around the axis as shown in the diagram? If you want, pause it and try it. If you want, I'll give you a hint. It says total, right? So the game plan is find the moment of inertia of this ball, find the moment of inertia of this ball separately, find the moment of inertia of the rod, and then add all of those moments together. So let's do that. Let's handle the rod first. All right, so the rod has a mass of 1 kilogram and it is 0.5 meters long. So here is, the L, that's like in the reference table, 0.5 meters. We want to know what is the moment of inertia of the rod. Okay, so we look in our reference table. It's the rod about an axis that goes through the middle. So it's going to be I is equal to 1/12 ml squared. Okay, that's right in the reference table. I is equal to 1/12 times the mass times 0.5. Don't forget to square it. So the moment of the moment of inertia of the rod is 0.02083 repeating. So for now, we'll call it 2.083 repeating, I guess, times 10 to the negative 2. What are the units for I? If you forget, look up here, it's kilogram. This is still measured in meters squared. All right, so kilogram meters squared. Nice. So that is one of 3 parts. But really, the balls are the same. So let's just do one of them because they're the same. So this is for the ball. And we're going to treat it like a particle. So that is actually also given to you on a reference table. It's all the way on the left-hand side of that table. So the mass of each ball is 1 kilogram. We're just doing one at a time though here. And the radius, oh man, what the heck is the radius? You mean I have to think now? Oh man. Well, the length of the rod is 0.5 meters. So let's just focus on this ball. Can you see? What is it going to be? What is the radius? This is still the axis of rotation. How far is it from the axis to that one ball? It's going to be half of the length, right? So 0.5 divided by 2. Oh man, I gotta think about it, and I might, it's easy to just plug in the numbers that they did not even read the problem or think about it. Sometimes that happens. Sometimes that happens. All right. So we got that, and we're looking for the moment of inertia of the ball. Now, I'll tell you what, I'm going to forget already that there's a second ball over here. I'm just going to add those 2 together. I'm going to try not to forget that there's 2 of them. Okay, 2. All right, so I is equal to mr squared. I is equal to 1 kilogram times the radius, which we very cleverly took the length of the rod and divided it by 2 because that's how far it is from one of the balls to the axis. And you get 0.0625 or 6.25 times 10 to the negative 2. Units again, kilogram meters squared. Okay, so the problem asks, what is the total moment of inertia? So the total moment, I could have left that. I total is equal to, we said it was one of the balls, I ball 1, plus the second ball, I ball 2. They're identical, so we were lazy and didn't calculate the same thing, exactly the same thing twice. But, in this case, that's okay. Plus the moment of inertia of the rod. So I'll just plug in the numbers. And you just add them all up. So the total moment of inertia is 0.14583 repeating, which is 1.46 times 10 to the negative 1 kilogram meter squared. Nice. Great. Now we know about the moment of inertia, and we can use this to do Newton's second law. But we want to practice more with because this is a whole other thing. We didn't have to calculate the mass before. And for each object, it's a different equation. So this lesson's all about practicing calculating the rotational mass or the moment of inertia, and getting used to that before doing the next thing, which will be Newton's second law, but for rotation. Anyway, that's about it. Thanks for watching, and have a great day.